So welcome everyone. Today we are very happy to have Atish Dabholkar from ICTP, and he's going to tell us about three avatars of modularity. Over to you,
Okay,
Atish.
thanks Abhijit and friends. I think it's really great to be back to TIFR, even if virtually. And you know, we were just talking. I was also talking. It just occurred to me when I was writing to Shiraz that it's almost surreal, to be talking about holography and modularity, given what is going on in the, sort of unfolding outside. But okay, one has to keep at what we do and pray for the best. So I think some of you have actually, maybe Sunil, this may be a repeat for you. Some of you have heard some of this talk, actually, much of this talk. I don't have much new things to say. So these are the three avatars of mock modularity. And this is based on work done with, this mammoth paper that we wrote long time ago with Murthy and Zwegers. Then some work with my student Diksha Jain, who is actually coming as a postdoc to Tata Institute, and Arnab Rudra, who was a postdoc at ICTP, who is now he is in India at ICER, Bhopal, and then Putrov and Witten. And there is some ongoing work that we hope to finish soon with Francesca Ferrari and Diksha. So anyway, but that's still in the making. So these are my distinguished collaborators. Pavel is well, okay, Zwegers and Witten don't need introduction, but Pavel is a colleague at Tata at ICTP. Sorry, you see, I still haven't.
That's nice.
Okay, so some of you have heard parts of this, and the point of my talk would be to put in all these things together and just to give you a more complete story of how mock modularity is appearing in physics and where it is connecting. I think it's coming in more and more, and there are all kinds of very interesting connections. But let's start historically. In Ramanujan's, and I know that many of you, I mean, the younger generation, they were not well trained in modular forms and worldsheet techniques. They started directly with holography and things like that. So I'm going to do a very kind of a pedagogical thing just to set up the questions. And if I even get to that, I think I'll be happy. And then try to give the solutions to these in three different contexts where mock modularity appears. So in Ramanujan's famous last letter to Hardy in 1920, he gave 17 examples of what he called as mock theta functions. And mock refers to the fact that they are not really theta functions. And he found very interesting hints of modularity. And so one of the functions is this one, some q to the minus 25, okay? And if any one of us normal human beings looked at this, you would not find any sign of modularity there. But Ramanujan, being Ramanujan, understood that there is some very deep symmetry behind this function. And despite much work by many eminent mathematicians, this fascinating symmetry, just a second, just let me keep up track of the time. When did we start? 40, okay. So I can go till, I have to really leave at 45 because I have another meeting at 13. So, so despite much work, this fascinating hidden modular symmetry remained mysterious for almost a century until the work of Zwegers, who was actually a graduate student, a former graduate student of one of my collaborators, Zwegers. And he really understood finally in 2002, what is mock modularity. And roughly speaking, a mock theta function is almost modular. Now, it's always very difficult to characterize. When you say something has a symmetry, it's very easy to characterize that it remains invariant under something. But if you say it is almost circular, it's very difficult to characterize. Is it a little bit circular? Does it have a wiggle, or what? In what sense is it feeling to be circular? So that's why characterizing mock modularity was difficult. So before going to mock modularity, let's first understand modularity, okay, which is like, let's first understand what it is meant by being circular. So just to remind you, a modular form of weight k is a holomorphic function on the upper half plane, which is essentially very symmetrical, and it doesn't change under this very large group of transformations up to some weight factor. So basically, it's a function that is invariant under modular symmetry. In particular, it's invariant under shifts. So you can do a Q expansion, and you can write it in terms of Fourier coefficients A and Qn. Now, where does modularity appear? So this is a very simple one-page summary of modular forms. And they appear in physics in three different contexts. One is in holography. In particular, in ADS3 quantum gravity, the modular group SL2Z in ADS3, if you recall, ADS3, Euclidean ADS3 is like a solid cylinder. And if you're doing some trace, a thermal ADS3 or a trace, then you're identifying these two ends. And it's a solid cylinder, so the boundary is a torus. And since in ADS space, only thing that matters is a conformal structure of the metric. You basically have boundary global diffeomorphisms up to wild transformations, which is just the SL2Z transformations. Then another SL2Z is that we are familiar with is the famous duality group of four-dimensional quantum gauge theories, or some congruent subgroup of SL2Z, which is the S-duality group of, say, n equal to 4 super-Yang-Mills theory. And then in topology, it appears because if you're computing some elliptic genus of some manifold, you can reduce that computation like a K3 manifold. Then you can reduce that computation to a two-dimensional conformal field theory calculation. And there, the SL2Z is the mapping class group of the two-dimensional torus world sheet. And therefore, physical observables in all these three physical contexts are expected to exhibit modular behavior. So why is modularity so powerful and so important in physics? I mean, we all know that it has played a very crucial role in early days of string theory. It continues to play a very crucial role in duality. In all kinds of contexts, modularity has been very powerful. And the main simple way to understand it is that the modular forms are highly symmetric functions. And this is summarized by a very powerful theorem that the ring of modular forms is generated by two Eisenstein series E4 of tau and E6 of tau. So ring meaning what? If you take a modular form F and another modular form G of weight K and weight K prime, then you get another modular form of weight K plus K prime. This just follows from the symmetry properties. If you just did a SL2Z transformation on both sides, it's clear that the weights will just add up. And therefore, it forms a ring. Ring meaning you are allowed to multiply, and it preserves the modular structure. But the powerful thing is that you need to know only two modular forms, basically, in your life. Because given any other modular form, let's say you want to find out the weight 12 modular forms, then the meaning of this statement is that there are only two combinations that you can think of: E4 cube, such that it has weight 12, or E6 square, which has weight 12. And any weight 12 holomorphic modular form, therefore, has to be of the form A times E4 cube plus B times E6 square. And now you can see that on the right-hand side, you have infinite number of Fourier coefficients, but it is completely determined by just knowing these two numbers. If you figure out what is A and B, then you know what that modular form is. So if you somehow know secretly that some function is modular, then you don't need to know all its infinite Fourier coefficients. It's sufficient to know just the first few Fourier coefficients. And in fact, this is the power that this was sort of the behind a lot of the magic that Ramanujan was able to perform. And this is something I learned from my number theorist collaborator. I mean, he also works a bit like Ramanujan, that you can basically, given any function, you can just do the first Fourier coefficient expansion, and you figure out the right coefficients A and B just by comparing the first few Fourier coefficients. And then that function is completely determined. And then sometimes you can write kind of magical identities proving that one function is equal to some other function, which just looks totally different. But you are able to do that. I mean, the simple example that you know is, for example, the Jacobi-Obtuse formula, which tells you the theta function, which is a sum as a product. They look totally different, but because they have a modular property, you can just write down that without doing a proof, in a way. So the proof is actually two-line.
Atish, sorry, one question. So what is the analytic structure of these modular forms in the tau plane?
They're holomorphic. They're completely holomorphic without poles. Also, they don't have poles even at infinity. Of course, the ones that you encounter in physics are not like that, but I will come to that.
Sorry, somewhere they need to be non-analytic, right?
No, I mean,
otherwise they will be constant or not. Sorry, because they're unbounded or something.
Yeah, like a cusp form. Let's take the product q pi 1 minus q to the n to the 24.
Okay. And sorry, and if you allow for non-analyticities like poles, etc., does this space become very, very big?
Yeah, this space can become very big, but basically you have to use this cleverly to extract the information that you want. Usually there is enough guidance to you about what should be the pole structure, and then you can, in many situations, and some situations not. So you have to.
Abhijit, basically, if you know what the poles are, you can find it by writing rational functions of these same things.
Yeah.
These
in
are
many cases,
in
many cases you can do that. Yes,
yeah.
In many cases you can just do rational functions and you can do that.
Okay. Thank you.
That's how we actually encounter it in physics. You will see in an example very quickly. So modular symmetry, but in physics point of view, modular symmetry is powerful because it relates f of tau to f of minus 1 upon tau. So from a two-dimensional conformal field theory, it relates high temperature to low temperature, or strong coupling to weak coupling. And this underlies the famous Cardy formula, because you can then do relating low temperature to high temperature. You can derive the asymptotic growth of states. But in fact, there is, as you perhaps know, there is a very beautiful exact generalization of the Cardy formula, which is the Hardy-Ramanujan-Rademacher expansion, which gives you the Fourier coefficients exactly in a convergent expansion. And this actually became important in physics. As you saw, I had described this in a few at schools also, in computing the quantum entropy of black holes, because the Cardy formula roughly gives you, which is the exponential of something, the Bekenstein-Hawking entropy of a black hole. But if you want to calculate the quantum corrections to the Bekenstein-Hawking formula, you need to go beyond the Cardy formula. And that's where actually this powerful machinery of modular symmetric becomes important. And you can use this Hardy-Ramanujan-Rademacher expansion. And they match on to, from the holographic side, from the black hole side, to corrections to the Bekenstein-Hawking formula. So now, having given you a brief summary of mock modular forms, let me now tell you what are mock modular forms, because it's a notion that has been talked about, and it's, so let me just give you a kind of a simplest definition. There are, you can add more bells and whistles, but a definition of a mock modular form involves a pair f and g. It's not defined just by one function, where f of tau is a holomorphic function on H, with at most exponential growth at all the cusps. Cusp is like a tau equal to infinity, imaginary tau. And g tau is a holomorphic modular form of weight 2 minus k, such that the sum, this sum, f hat, which is equal to f tau plus g star, I'm going to tell you what is g star, transforms like a holomorphic modular form of half integer weight k of some congruence. So it's a slightly more convoluted definition. But the main point is that there is some kind of anomaly which makes it impossible for you to have both holomorphy and modularity at the same time. So the function f of tau, which is what is called the mock modular form, this is the kind of function that Ramanujan was talking about. It's perfectly holomorphic. It's a nice holomorphic function. If you remember my first example, it had an expansion in q, powers of q, not q bar. Q is e to the 2 pi I tau. There was no power of q bar appearing. So it's like a very nice holomorphic function, but it has no obvious modular properties, except if you're Ramanujan. G is called its shadow. It is both holomorphic and modular. And F hat is called the modular completion, which is modular. So you restore all this beautiful symmetry, but then at the expense of being holomorphic. So the F hat is no longer holomorphic. F is not modular. G is holomorphic and modular, but actually G does not completely determine F. So that's why it was so difficult to wrap your, wrap around this.
Sorry.
Atish, what is G star?
Atish, G depends on both tau and tau bar, is it?
No. G depends only on tau.
But what is G star?
Yeah, I'm going to now explain. And suppose G has some expansion like Qn. Then from this, I'm going to give you how to construct G star in one. So given Bn's, you can construct a G star such that F plus G star becomes modular magically.
You haven't told us yet what is G star. It's
Yes,
just something that you're going to construct from G.
Yeah, and it's going to be a simple. So F tau has a Q expansion, G tau has a Q expansion. However, F is not modular, G is modular, but what we really need is G star, which is not modular and it is not holomorphic. So this is like exclusive OR. You can have either holomorphy or you can have modularity, but not both. It's a little bit like anomalies, that you can either have chiral U1 or you can have gauge symmetry. If you preserve gauge symmetry, then you break chiral symmetry.
Sorry, Atish.
Yeah.
One question about the previous slide.
Yeah.
So given G, you are saying one can find F, not necessarily unique F, so that F hat is modular, right?
No, that's not true. I mean, what I'm saying is that unless you are somebody like Zwegers, generically given G, you cannot find an F. You somehow need to know F and G together.
Okay. But there are instances where for a G, multiple Fs may exist. Is that also?
No, it is clear that it will become clear that in fact, there is always a multiple F exists.
Because you can just add F, which is modular.
You can add F, which has a holomorphic.
Okay.
Then you can define a notion of optimality to restrict. Yeah. Okay.
I see. So modulo, if you don't want to, if you mod out by that freedom, then sometimes there is
then many times it is unique. Yeah, but there is no general theorem that given any G, I can always construct an F.
I see. Okay, thank you.
Okay. So the function F is holomorphic but not modular. The function F hat is modular but not holomorphic. Okay, that's the simple summary of mock modularity. It's an exclusive OR, and this incompatibility, and which is why it is subtle, like anomalies, it has been a subtle thing to wrap things around it, because you try to preserve one thing and you fail to do the other. And in fact, you can actually characterize the whole mock modularity discussion from a physics point of view as a holomorphic anomaly. It's not exactly the usual kind of anomaly, but it is a kind of anomaly, as I will explain. The modular completion, which I said, the F hat of a mock modular form is related to the shadow by a holomorphic anomaly equation. And it is given by this equation. Basically, if you take the tau bar derivative of F hat, it is not zero. However, the failure is captured by the shadow. It basically given by, take the shadow and take it complex conjugate. So G tau bar is basically Bn bar Q bar to the n. And the non-holomorphic correction G star by itself is not modular. Now, from here it's clear that you can reconstruct G, because this is a very simple equation. Del by del tau bar is something. And del by del tau bar you can invert. It's an operator that you can invert. It's just, you can write down a kernel very easily. And that's how you can reconstruct G star up to this, what Abhijit talked about. You can always add to that construct any holomorphic function and it would not change things because any holomorphic function would be annihilated by del tau bar. So the kernel of this del by del tau bar is a kind of a freedom that you have in reconstructing G bar. But other than that, you can reconstruct it. And actually, there is a very explicit formula. And I just want to give this explicit formula. It involves the incomplete gamma function. And G star basically is given in terms of this somewhat complicated looking function, b bar of n q to the minus n, and the gamma function which depends on tau 2. But one simple way to remember is that basically the gamma function appears because you're sort of trying to invert del by del tau bar acting on something as a delta function. No, it's like a Green's function for the operator del by del tau bar. So roughly speaking, these are what you're doing is finding the Green's function for this operator. Okay, and this is the solution to it. Now, actually, the incomplete gamma function will make its appearance, and in fact, it appeared in some of the work that Sunil did many years ago with Imbimbo, and it appeared in index theory, in the Atiyah-Patodi-Singer index theory. This incomplete gamma function appears when you define the eta invariants, and it also appeared in some other Kalias index theory. So this is appearance of this incomplete gamma function is actually going to be the key to make these various connections with physics, and when we try to get a path integral derivation of this, and that's how mock modularity we can understand from a path integral point of view. So that's going to be another theme of my talk, is that we want to understand mock modularity both where it appears in physics and understand it from a path integral perspective. And we actually can understand it completely in some cases. So just to summarize, mock modularity is like a failure of something being both holomorphic and modular. You know, it's a little bit like if you want to have something which is both blue and circular. So circular is like a very nice symmetry. You rotate it and it remains circular. So that's like modularity. But then you want to insist upon holomorphy, which is like you add one more property that it should be blue. And if you look at this figure, this is either blue. You can remove this red piece, then it becomes blue. And then it is circular. Or if you remove this red piece, it is blue, but it is not circular. So roughly speaking, the function f that you're talking about is like this. And this little piece that you're adding is g star. And this whole function is like, the addition is like a f hat that I talked about. And this g star in turn is constructed from a little circle, which is a g tau, which is really a blue holomorphic modular form. So this is a kind of a rough, I mean, actually a pretty good, I would say, geometric analogy.
Atish, one question. So this equation that you wrote down, which was del by del tau bar of f hat is equal to g bar, right?
Yeah.
And this equation, given that g is some holomorphic modular form, probably make sure that f also should be a modular form, not holomorphic, but a modular form, right? Then what is the obstruction in solving this equation in general for a given g? I mean, just to kind of understand, because you said that not all g's lead to mock modular forms, right?
Yeah, it may be that, no, you are right. In a certain way, you can do that. Yeah, whether the question is whether you get something interesting for f. Yeah, there is a kernel. There somehow the f belongs to the kernel of this equation. That kernel could be such that it's kind of empty. I mean, or it doesn't have anything interesting in it. Or it has only modular forms in it, and not mock modular.
No, I mean, given g, this is an inhomogeneous equation that you would have to solve, right? So is it that one cannot? There's some obstruction for some cases.
No, I think it's not so much the obstruction, but whether you can get interesting objects out of it.
No, I mean, this question would be relevant to answer, you know, what is the space of such functions, whether it's some ring or not, just like modular form.
No, it's definitely not a ring. It's definitely not a ring, because when you multiply, because you're adding two things, the ring structure actually doesn't work.
Okay.
So, okay, it might work if you expand your notion of mock modularity to mixed mock modularity. So actually, that's one of the obstacles. I will come to that in a moment, okay?
Okay.
So, okay, now let me quickly remind you of Jacobi forms, okay? And now, sorry to be throwing so much mathematics at you, especially if you haven't been doing these things on the world sheet. This is a one generalization of modularity when you add one more variable. Okay, there is a variable z. And one way to think about it is that if you have a torus, if you have a toroidal world sheet, and this is a tau parameter, then you can think of z as a coordinate on the torus. Okay, so if you can define sometimes a function, a trace, on a torus with something inserted at z, and that's why that object comes out to depend on tau and z. So it's a function of two variables. It's a Jacobi form of weight k and index m. And basically, again, it's roughly highly symmetric under modular symmetry. And it is highly symmetric under elliptic symmetry. See, elliptic symmetry is simply that if you have a torus, you can think of it as being obtained by modding out the upper half plane by a lattice, so by shifts. So you want a function, if you want a function to be well defined on a torus, it must be roughly a doubly periodic function on a complex plane. But of course, it's not possible to have a doubly periodic function which is holomorphic. There are theorems like that. So the best you can do is that sort of is doubly periodic up to a phase. You know, it's some kind of a section of some bundle or something. But with these properties, you define Jacobi form. So it's basically modular and elliptic. It has this double symmetry. It's symmetric under double translations on a torus, on a complex plane, and it is modular. And therefore, its Fourier expansion now is given in terms of these two coefficients. And it occurs very naturally in physics context when you're computing elliptic genera. So people, when they did work on holography and various black hole story, we're computing the elliptic genus of some conformal field theory, and it appears in many contexts. So if you consider a conformally invariant nonlinear sigma model, so for example, if the target space is K3, it's a conformally invariant nonlinear sigma model because K3 is a Einstein manifold. I mean, it satisfies, it's Ricci flat, and therefore the beta functions are 0, and it's a conformally invariant nonlinear sigma model. And then you can define this trace in the conformal field theory, which is, it has a left moving and right moving super conformal symmetry, which means that in addition to your T and T bar, which are the Virasoro generators, the energy momentum tensor, you also have currents J and J bar, J left and J bar right. And so you can define, and there you can define their charges of these to be F left and F right. So given this, and the Hamiltonian is basically the usual Hamiltonian, so you can define the normal trace that you do with the insertions of these operators. And this is where Z appears. So e to the 2 pi I Z F left, where F left is the charge corresponding to the left moving current. And what this does from a physics point of view, it computes the right moving Witten index of the right moving ground state. So if you think of a conformal field theory is a 1+1 dimensional theory, living on some string or one brane, then you can have arbitrary oscillations of this one brane, which are only left moving, going up and not going down. All the downgoing oscillations, which is like right moving oscillations, they are all in the ground state. And this is what this elliptic genus computes. Now, once again, because of the symmetry, there are so a very simple example is take the elliptic genus of T4. It's a weight -2 and index 1 object with theta. These are the usual theta functions. So let me just remind you, this is basically looks like pi 1 minus q to the n square 1 minus q, y inverse square divided by pi 1 minus q to the n to the power 4. This. And this you will recognize as 4 bosons on the world sheet and 2 complex fermions which have charge one way, psi and psi bar. And that's why you get a square, I mean psi I bar. And this object turns out to be a Jacobi form. So the Jacobi forms are not some very exotic objects. You encounter them all the time in your calculations. The elliptic genus of K3 is another such Jacobi form of weight 0 and index 1. Now, once again, the ring of Jacobi forms is also, this was a theorem by Eichler and Zwegers, that is again generated by this A and B. So basically this A and B, which are very natural from the physics point in the context, they are the elliptic genus of conformal field theory whose target space is T4, and elliptic genus whose conformal field theory target space is K3. You just calculate those, they turn out to be given in terms of this Jacobi theta functions. Theta 1 square, theta 2 square, if you don't remember, but theta functions are roughly just products like that, 1 minus q to the n, 1 minus q to the n y, 1 minus q to the n y inverse, where y is e to the 2 pi I z. Okay, so these are products like that. So this is a very explicit expression you can write down. And then the powerful theorem is that just knowing these functions, you know everything about Jacobi forms. Because once again, like E4 and E6 for the modular forms, you can write down, suppose you want a weight 4 index 2 Jacobi form. How will you do it? What are the possibilities? Well, you want weight 4. So the only possibilities are, just by looking at it, sorry, you want index 2. So since you want index 2, the only way you can get an index is by taking a square or b square or ab. There are 3 possibilities, a square, b square or ab. However, this has weight minus 4, this has weight minus 2, and this has weight 0. But you are looking for something with weight 4. So it's easy. You just multiply this by E4 square, which has weight 8. So 8 minus 4 is 4. E6, which has weight 6. So 6 minus 2 is 4. And E4, which has weight 4. So this is basically the only possibility you can have. And there are 3 coefficients and you're done. So in many of this, the power again comes because of the fact of these theorems like that. So in fact, the same is true for the elliptic genus of K3. You know, you can do an orbifold calculation to get this. But if you know that the elliptic genus of K3 is a weight 0 index 1 Jacobi form, then you don't even have to lift your pen. You know what the answer is, because there is a unique Jacobi form with these properties, and it is this. So you immediately can calculate many things without actually doing a physics calculation.
Atish, one question.
Yeah.
So what are we assuming about the analytic structure here when we say
holomorphy.
Holomorphy in tau or z?
Yeah, holomorphy in tau in the upper half plane and holomorphy in z in the upper half plane. No
but
poles.
The examples that you had, that did have poles, right? I mean, the next page has poles in Q. Sorry, in tau or whatever. I mean, you have eta to the 6 in the denominator here.
No, but it's cancelled by this.
Sorry, this expression here.
Q to the.
Sorry. There is some poles in there seems some poles, right?
Yeah. Okay. Let me think about it. Just a second. You may be right about that. Yeah, this has a pole at Q equal to 0. Yeah, at the cusps, it has a cusp.
But how about this infinite series of poles here?
No, it doesn't have infinite series of poles. No, only at Q equal to 0.
Sorry, maybe I'm mistaken, but it seems like 1 minus q to the power n to the 4, right? That's what you wrote down here above.
Here.
Yes. So what is happening there? That let's say nth root of unity or something.
You're worried about no, but see, no, there is no pole here, right? I mean, this 1 minus q to the n, like Q24, like the bosonic string doesn't have any poles at Q equal to 1. It has pole only at Q equal to infinite, Q equal to 0.
Sorry.
Q equals 1 is tau equals 0, right? So we are on the boundary of the.
We are on the boundary here. Yeah. Upper half plane. Sorry.
But it does have.
Yeah, it does have. Yeah, you're right. Sorry, you're right.
It's just that they are not in the region.
Yeah, it's not a tau equal to 1. That's what I want to say. In the upper half imaginary tau plane, there are no poles except that tau is equal to I infinity, which corresponds to Q equal to 0.
Oh, I see. Okay.
Yeah, sorry.
Okay.
Yeah, you should either think in terms of the Poincare disk or the upper half plane.
Okay.
So in the upper half plane, holomorphic. It can have. In the upper half plane, there are no poles.
Okay, so no, just no poles in the upper half plane, right?
Yeah,
okay.
No poles in the upper
half. And then by physics, why do we expect the elliptic genera to have such a property? Because only then your machinery of a ring will be applicable, right?
No, that's very easy to understand from the physics point of view. Why? Okay, the elliptic genus has to be for the simple reason. I explained it actually. I went over it quickly. See, conformal symmetry follows. From the conformal symmetry, you know that the path integral has to be modular.
Yes.
Because if you use a diffeomorphism invariant regulator, which you can always do, like a heat kernel or something, right? Then if it is while invariant, then it is conformally invariant, because conformal group is nothing but global diffeomorphisms up to while symmetry. So if you have a diffeomorphism invariant regulator for the path integral and the theory is while invariant, then it is modular.
Sorry, no. The question is, why should we expect it to be holomorphic in upper half plane?
Because because it's a trace, right? It's like
But
e to the minus beta h, right? If
but
you have a
that's
canonical ensemble,
okay.
you don't expect
characters of a
weird
CFT
things happening
are
at some finite temperature, right? See, tau is like a temperature.
Yes.
So you can have weird things happening at some imaginary infinite temperature, things like that, but you don't expect weird things happening at finite temperature.
It's just like the characters of a 2D CFT, which are completely holomorphic in the interior of moduli space.
No. Yeah. So that I understand that, but from first principle, let's say I don't know anything about the theory. Why do I assert that the elliptic genus has to be an holomorphic function in H, and that's why then like let me just play this game with the weight and index and find the coefficients. Only then I can play that game, right?
I think you can prove from the fact that it's a convergent trace. I mean,
no, but why does convergence? It could be a finite radius of convergence, right? I mean, it could have some poles in the bulk of the upper plane. Let's say tau equal to 15. Who told me anything about tau equal to 15? Tau equal to I15 or something.
But your argument then is even for an ordinary 2D CFT character, it could be diverging in the upper half plane, right?
No, I'm just an abstract conform field theory. Why is such a thing not possible?
Yeah, I think the reason is that see, you're basically computing e to the minus beta en
with a phase,
where ens are all positive.
Yes.
With a phase multiplying Atish.
And with a phase multiplying it, okay, there is a phase multiplying it, but this is highly convergent, you see. As long as beta is positive and ens are positive, you don't have. That's why in an ordinary canonical ensemble, right, you don't get a singularity at some finite temperature.
Sorry, but this would be a statement of convergence near
this is imaginary part of tau, right? Beta is like imaginary part of tau.
Right. So at imaginary part of tau equal to infinity, sorry, at imaginary part of tau equal to infinity, yes, I can see that if we have such a thing, then it would be convergent. I agree, but the convergence could be in a finite radius. Why should convergence be true to entire upper half plane?
It's not, right? I mean, why it is convergent for all beta this thing.
Yeah, it's convergent for all beta positive, right?
Maybe is it a statement?
Why? I mean, there could be lots of degeneracy, right? The degeneracy can grow a lot, so there could be phase transitions and whatnot. I don't know. I mean, go ahead, Sandeep.
No, what I'm saying is that as it becomes better and better convergent as beta increases. That's clear, and it's highly suppressed exponentially.
There must be a formal proof. I think.
There must be a formal proof. I mean, I don't know how do you prove in canonical ensemble that at finite.
No.
Okay, there can be a phase transition. Okay, you are saying that the number. I think you can put some conditions like if the density of states grows in some Hagedorn way, then
That's what I was going to suggest, that with some reasonable assumption on the density of states growing with energy, you should be able to prove it, right?
Yeah, basically if the density of states grows faster than e to the minus beta e, right?
You can actually bound the growth of density of states in a CFT by just the fact that if you know some chiral algebra, without null vectors, the maximum growth is whatever. I think that kind of argument should be
just
enough.
From the central charge and the energy, you get
I would think,
right? Because
Okay, I would have to think, because it's
but
not
I think
quite clear why this says anything
right?
about poles at finite distance.
But I think in a reasonable conformal field theory, if the density of states, I think one can prove this probably quite easily. If the density of state doesn't grow exponentially, right? Then if it is slower than exponential, then this series will be always convergent for positive.
Also, if it diverges for some small value of tau, then by modular transformation, you can convert that to a large value, right? So I think it seems very unnatural, because you could create lots of divergences by modular transformation starting with any one.
Sorry, just give me, maybe I'm mistaken, but let me just give you an example. So what if, what if the density of states is like, let's say energies are integers, 1, 2, 3, 4, okay, and the density of state is 2 to the power n, okay, just for the sake of it. Then you would get, this is a geometric series, you can sum it, right? Sure. And then you would get 1 over 1 minus, 2q.
Yeah, because I think the density of state is going as e to the power n log 2, right? Yeah, so it's exponentially growing with energy.
Yeah, and that's what I think is
that is the Hagedorn behavior.
Yeah. But I think I don't think you can have that, no, in a normal, at least in a CFT.
See, basically you have rho e to the minus beta e.
No, so the question is whether density of states grows as like e to the rho, e to the...
I see. So it needs to go to like a square root rather than exponent. I mean, square root.
It goes as e to the beta naught e. And we know that for Cardi formula, it goes as a square root of the energy.
Okay, fine. Thank you. Yeah, so that maybe you can show that you cannot have poles. Thanks.
Okay, so now I'm sorry, I really have a cutoff at 12:45. So normally I would have not had a cutoff, but today I do. So I need to rush up a little bit. So basically using this elliptic property, you can take out the Z dependence completely and write it as a sum over theta functions. So this is called the theta decomposition. So instead of thinking about a Jacobi form, which is a function of two variables, you can basically take out all the Z dependence out in the standard theta functions. These theta functions are well defined, and they basically make sure that everything is doubly periodic with the right phases and so on. And what you're left with, and then some vector of modular forms. So therefore, a Jacobi form of weight k and index m is exactly equivalent to a vector of modular forms, a vector valued modular forms of weight k minus 2, because the theta function has weight half. Okay, so this is a very nice theorem that instead of thinking about Jacobi forms, you just think in terms of the vectors of the. So a lot of the properties of the modular forms you can use, except that you have to deal with a vector of modular forms. By vector of modular forms, I mean that when you do a transformation on it, the transformation will mix the components of this vector. So you have some linear matrix. If you suppose you tau going to minus 1 upon tau, then you will get some transformation that HL of minus 1 upon tau will be some matrix AL prime, HL prime tau, rather than coming back to itself. It's a little bit. Okay, so this is a mathematics introduction. Now let's come back to.
Sorry, so it's always a vector of dimension 2m given by the weight. Huh?
Yes, always a vector of dimension 2m given by the weight. Exactly.
Thank you.
Now, so far so good for the mathematics. Now, this was a very nice quote of Freeman Dyson, that my dream is that, so Freeman Dyson gave this very beautiful talk. I recommend that you read it if you get a chance. Walk through Ramanujan's garden. It's a very nice article on the website. And actually, I remember I was a student in 1987. A graduate student from India, and it was really, I mean, Ramanujan is of course an inspiring figure. And Dyson said like this, that my dream is that I will live to see the day when our young physicists struggling to bring the predictions of superstring theory into correspondence with the facts of nature will be led to enlarge their analytic machinery to include not only theta functions, but Mach theta functions. And I never thought that Mach theta functions, I will ever deal with them. But they sort of came in a very important way. And okay, we are not yet making contact with the facts of nature, but they come in a two very important contexts which we have understood as some very fundamental properties of string theory and also quantum field theories, namely holography and duality. So somehow in dealing with holography and duality, we were sort of naturally led into the world of Mach modular forms 10 years ago. So you never know what mathematics is going to become important. And this puzzle was the following, that some of you have seen me given talks on this, that some counting function for the degeneracies of some special quarter BPS black holes in some particular compactification of string theory is actually given by a meromorphic Jacobi form. So meromorphic because meromorphic in Z. So because this goes as, if you remember a tau of Z, it goes as theta square of Z. And therefore it has a pole at Z is equal to 0. Double pole at Z is equal to 0. And in fact, it has a pole at all the images of Z is equal to 0 in the complex upper half plane. So this is a function which has poles all over the place. And the claim was that from the physics side, people had, there was a nice papers by Dijkgraaf, Verlinde, and so on, who claimed that the degeneracy should be given by this function. But this just simply could not be true, because since there is a double pole, it will matter, the Fourier coefficients are not well defined, even though the counting function is well defined. The Fourier coefficients are not well defined, because if I take a contour here or a contour here, I will get two different answers. So there must be something wrong with the counting. So what is wrong with the counting? That's the question. And the answer to this question will turn out to involve mock modular forms. Then there is another puzzle with instantons, that instantons, a physical way to say that is that suppose you are interested in D4, D0 bound states. You take a D4 brane wrapping a K3 or a D3, D minus 1, okay, D4, D0 bound states. So you take a D4, Euclidean D4 brane wrapping a K3 times a circle and a D0 brane. Then the bound states are basically given by instantons. There is a Yang-Mills theory if you have some D4 branes, and there are instantons. And these bound states are given by the Vafa-Witten partition function, which is some twisted partition function of this conformal field theory, which basically computes these bound states or the number of instantons. So basically, the path integral reduces to an integral over the Euler to calculate the Euler character of the instanton moduli space. And if you now, there is some, this is the twisted gauge theory. And by twisted gauge theory, what you mean is that you have a supercharged Q, but you sort of reassign the R symmetry charge. You sort of use the R symmetry charges. You use the R symmetry and the space-time symmetry and mix it together, such that the supercharge, which normally is a spinner under the space-time symmetry, and it transforms in certain way, like in this case, n equal to 4 supersymmetry, it transforms as the 4 of SU4. So you can choose some particular subgroup of this SU4 and your symmetry group, which is SO6, space-time, SO4, space-time symmetry, in such a way that Q under that, so you basically find some new subgroup SU2 prime under which, or SO4 prime, sorry. So you find an SO4 prime, which is a subgroup of SU4 cross SO4, such that Q transforms as a scalar. So it doesn't have any, so therefore it can square to 0. So normally, if you know, Q square gives you Hamiltonian, but here it squares to 0. And using that property, you can show that d by d tau bar of the partition function of these instantons is Q acting on something. And since Q squares to 0, so basically you can argue that this has to be 0. And this holomorphic, therefore the partition function has to be holomorphic. And it should receive contributions only from instantons. And moreover, it should be SL2Z invariant if S duality is a symmetry of the quantum gauge theory. And Vafa-Witten noticed this actually in 1995, that if you calculate the partition function of Yang-Mills theory on K3, you actually get a very beautiful answer. You get this famous 1 over Q pi product 1 minus Q to the n to the power 24, which you can immediately recognize as the 24 left moving bosons of the heterotic string. And this was actually before the type 2 heterotic duality. Now from the type 2 heterotic duality, we understand that D4, D0 bound states are dual to winding momentum strings of the heterotic string. And the heterotic string winding momentum string that is given by the 24 left moving oscillators. So this was a hint that doing a completely unrelated gauge theory calculation, you got the partition function of the left moving heterotic string. And they were really puzzled by this. But they were even more puzzled by the fact, but at least this has nice modular properties. And therefore, they took it as a success of the SL2Z as an evidence that quantum gauge theories actually do have SL2Z symmetry. But when they do the calculation on some other manifold like CP2, you find that the function is not modular. So now it cannot be that quantum gauge theory is SL2Z invariant on K3, but it is not SL2Z invariant on CP2. What is going on? So what is wrong with duality? And then another puzzle with elliptic genus is that if you take the elliptic genus of a superconformal field theory, it's again expected to be holomorphic by the general argument that I gave, okay, which we discussed now in detail. But it turns out that for a non-compact superconformal field theory, for example, a sigma model with infinite cigar as a target space, the holomorphic function that you compute is actually not modular. Now, this would be a major violation of the mapping class group and so on. So what is wrong with conformal invariance? Mapping class, it means that your conformal symmetry is not really true. And it turns out that all these three answers involve mock modularity from a mathematical point of view, and they involve a non-compact path integral from a physical point of view. So much of my work in the last few years was to first understand mock modularity from the mathematical point of view, or how it came in the black hole story. And some of the recent work was to really understand it from a physical path integral, how to explain that mock modularity. Now, the story for the meromorphic function is very nice, actually, and I will very briefly, in view of the time, actually, I should really rush. How am I going to finish it? Actually, I will...
You know, I'm thinking one possibility is we have you back, Atish. Because, no, seriously, rather than rush, because it's up to Abhijit and so on, but we could easily, at your convenience, have a special seminar. And, you know, it'll make it also nice for us to slowly understand these points, because you're explaining it so well. At least for me, it's a real treat. So okay. I think rather than just rush, perhaps my suggestion, Abhijit, is we allow Atish to close at an point, but please come back then, Atish. Sometime.
Yeah, that would be great.
I'll be happy to do that, yes. I'll be happy to do that.
But next time you come, you leave 2 hours for us, because you know how it is. You have to explain slowly and so on. We have a lot of questions like that. Okay. Anyway, but I think that's better, no, Abhijit?
Yeah. I think that would be very nice if you could do that, Atish.
Okay, I'll be okay. So I think there is I can stop at an appropriate time.
Yeah.
If I'm coming back, actually, I could even stop here. But okay, let me just tell you a little bit and then I will stop. Okay. So the way the meromorphy gets related to mock modularity, right? So first of all, what is the meromorphy to mock modularity? And the meromorphy actually has a very interesting physical interpretation. So what we found was that the counting function, which was some function of z and tau, some counting function, had poles in the z plane, which meant that if I took different contours, I would get different Fourier coefficients. Mm-hmm. Now, this didn't make sense, because if you really are computing the degeneracies of black holes, black hole degeneracy should be not independent of where you are. You should have a unique answer. But this was understood by the following way, that actually, even though the elliptic genus is kind of modular, in fact, depending on where you are in the moduli space of this target space, which is K3 cross T2 in this case. So depending on this target space moduli space, where you are, the answers can be different. And in fact, the moduli space is divided into chambers, and the chambers are separated by walls. So as you move around smoothly inside a chamber, the degeneracy doesn't change. But the moment you cross the wall, the degeneracy jumps. However, that jump in the degeneracy, you can actually relate exactly to, so there is a moduli space M, okay, with some moduli mu. Those moduli depend on this coordinate Z in a very specific way, or actually the other way around, the Z depends on the moduli in a very particular way. So as you move around mu in the moduli space, Z also moves. And when you cross the wall in the moduli space, you cross a pole in the Z plane. Okay, so there is a, am I clear here? So there is a mu space and there is a Z space. Mu space is the moduli space of your compactification. Z space is, Z is just some chemical potential corresponding to some charge. What happens is that one can actually figure out an exact map between Z and mu, such that when you cross a wall in the mu space, you cross a pole. So poles get related to the walls. And the residue at the pole gets related to the jump in the degeneracy. And in fact, in this story, it works out very beautifully that you can actually prove. And this was a story that took a number of years to understand. Myself and various group in Paris and Gayeto and Ashok and then Cheng and Verlinde. So various groups sort of worked on it together and from different points of views. And now we understand the story completely. That all the quarter BPS counting formula is very beautifully understood for the K3 cross T2. And there are walls and it jumps and all that is captured by this unique meromorphic Jacobi form. All that's very complicated structure is uniquely captured by the, and it is now it is clear from also from a dual. Okay, so let me not go there. But however, this is still surprising because if you're a black hole physicist, because one of the reasons why I was interested in this was to understand the quantum degeneracy of a black hole. But the quantum degeneracy of a black hole is entirely determined by the near horizon geometry of the black hole, which we know does not care about the moduli at infinity because of something known as the attractor mechanism. But in any case, the black hole horizon is some intrinsic property of the black hole. And we believe that the entropy of the black hole is telling us something really important about the microscopic degrees of freedom at the Planck scale of the black hole. And it has nothing to do with some asymptotic degrees of freedom. So how can such a really intrinsic quantity depend on the moduli? So that was the puzzle that I was bothered by. And the answer turns out to be very nice. Actually, what happens is that indeed the horizon properties are unique and intrinsic. However, when you cross the wall, what can happen is that on one side you have a single-centered black hole. On the other side, you have a single-centered black hole and a multi-centered black hole. And at the multi-centered black holes, as you approach here, the distance between them goes to infinity and they drop out of your spectrum. And therefore, the degeneracy here in chamber 1 is not the same as degeneracy in chamber 2, but this is the degeneracy of multi-centered black hole. So the degeneracy of the single-centered black hole does not change as you expect from quantum gravity. But the degeneracy of multi-centered black holes changes because the multi-centered black holes may or may not exist depending on the moduli. Now the question arises, the next question.
Sorry, Atish, sorry to interrupt, but couldn't it have been that for the same charges, there was more than one attractor solution? Is that a possibility?
Yeah, that could also happen. That could also happen, in which case there could be more, there could be other multi-centered solutions. So, but all of it should be understandable in terms of multi-centered solutions, because the fundamental principle is that the degeneracy of black hole should be completely intrinsic.
No, it should certainly not depend on the asymptotic values of the module.
Yeah, it should not. It should only depend on the charges and the. I mean, another way to say from the holography is that once the ADS, once you know that the near horizon geometry is ADS2 or ADS3 cross S2, it's completely determined by that geometry, and whatever parameters determine that geometry should determine the entropy of the black hole and not anything else.
Right. Okay. Thank you.
So then the question becomes, what counts the horizon degrees of freedom? And that's where the mock modularity comes into picture. And this is the decomposition theorem. This was the main result of this collaboration with Zwegers. And this was actually the question. This is an interesting story that, and I will tell you the story and I will stop. So I had invited Zwegers actually to a workshop in Paris, just on the hunch because we were using his book quite extensively. So we had invited a few mathematicians, and we were sitting in a Parisian cafe and we were talking about this. And I said, okay, how can it be that how can the counting function be meromorphic and so on? How do we define it? I was bothered by this. And I thought that, okay, talking to all these masters in Jacobi forms, we should figure out how to actually extract the Fourier coefficients in some unique way. Then he told me, no, this is a very difficult problem. It goes back 100 years to Ramanujan. But luckily for you, my former graduate student had just solved this problem a few years ago in 2002. So I thought, okay, we will start collaborating and more or less in 6 months we'll figure it out. But it sort of grew up because actually the mathematics was also not fully understood at that time. So it became a really kind of an interesting physics maths collaboration, number theory and black hole physics collaboration. And so we did actually get also new mathematical results. And one of the mathematical results which actually very nicely motivated by physics is that the meromorphic Jacobi form, which counts the degeneracies asymptotically of everything, can be uniquely decomposed between one function without poles, with poles, and another function without poles. The polar part is called the upper-Lerch sum and has exactly the same poles as this function on the left-hand side. So therefore, the difference between the two has no poles in Z. And that's the answer to my question, that what is the function that computes the horizon degrees of freedom? And that function is this function, psi m of f, okay? The finite part is free of poles and its Fourier coefficients are uniquely defined without ambiguity. And those are the ones which should give you the degeneracies of quantum black holes. And therefore, those are the ones which are really interesting. But because you are sort of taking a modular function and splitting it into two, you are not guaranteed that these two functions separately will be modular. And in fact, they are not. However, the failure of modularity is very precise. And you can show that this object is a mock Jacobi form. So the statement is that the single-centered black hole degeneracies in situations when you have wall crossing, which is actually the generic situation. Most of the situation, any generic Calabi-Yau, you will always have wall crossing. Generically, you will not get a Jacobi form, but a mock Jacobi form for the counting function of the single-centered black holes. And the Fourier coefficient of the mock Jacobi form give you the quantum degeneracies of the black holes. That's the statement with which I can leave you today.
Okay.
This is the, what is the call?
Okay, thanks, Atish, for giving us half the talk, and we look forward to the second part. Thanks a lot.
Great. Okay.
Thanks.
Thanks.
Let's all clap.
Thank you.
Thanks,
Beautiful
So
talk.
if there are questions, maybe we can take a couple questions. Is that okay, Atish?
Yeah.
Atish, I have a question about this Z being a function of mu, the moduli. Usually in field theory, for example, free field theory of compact bosons, we don't see chemical potential to be a function of the moduli. Could you give me some physical way of understanding why it should happen in the K3 times T2?
Because in a generic situation like that, there is no wall crossing. You see, so what you're saying is correct, that in situations like if you just took single K3, there is no dependence on the moduli because the elliptic genus is really a topological quantity which does not depend on the moduli. But there are situations, and generically, actually, for a generic Calabi-Yau, there are walls, and therefore that property somehow must reflect in the elliptic genus. So in that case, the elliptic genus is not going to be, will have some dependence.
So you need to have wall crossings for chemical potential.
Yeah, basically in situations where you have wall crossing. And actually also in quantum, in field theory, people have been computing this period of, in gauge theory, people are coming up, there are poles of this kind. And I think mock modularity is sort of lurking in many places. I'm sure Abhijit has also encountered them in various contexts of not in theory and so on. I mean, you generically get meromorphic objects, and then there is some mock story there, which is not always easy to figure out, but okay.
But when you say Z is function of mu, you mean a piecewise constant function of mu, right?
No, actually, okay, there is a map that you can give such that when you cross the wall, you cross a pole.
Atish, you gave a very beautiful explanation for why the choice of contour gets related to the choice of the asymptotic moduli, etc. But why is it that in the end, the single-centered entropy corresponds to something so close to a modular form, like a mock modular form? I mean,
very good. So the physics intuition is that actually there is a string. Yeah, why should it have modular properties at all?
yes.
Very good question. But you know that the single-centered black holes can sometimes be viewed as coming from a black string excitation. And there is an MSW string whose near-horizon geometry is ADS3. So even though the black hole near-horizon geometry is ADS2, there is a black string whose near-horizon. So this is actually the topic of the current work with Francesca and Diksha. That, yeah, very good question. That why should there be modularity at all? The reason for that modularity is that it has to do with ADS3. We have not fully understood this, but it's the SL2Z of the near horizon ADS3, which is a completely different SL2Z.
I see. I see. So it's the MSW ADS3 that somehow it gives rise to not a modular but a mock modular form.
Because the MSW conformal field theory, if it is non-compact, as I will explain, yeah, if the MSW conformal field theory was compact, then there is no way you can get mock modularity. But if you have some contributions coming from the boundaries of the field space in your path integral, then you can actually get mock modularity.
I see. I see. Okay. Beautiful. Beautiful. We really look forward to this then. Okay.
Thanks. Thanks. So I will coordinate. Sorry, I really have to run now. I'm already 5 minutes.
Okay. All right. Thank you.
Thank you. Thank you very much. Thank you.